All right, so now let's do an example using the following information. A new engineer is evaluating whether to use a higher voltage transmission line. It will cost $250,000 more initially, but it will reduce transmission losses. The optimistic, most likely, and pessimistic projections for the annual savings are $20,000, $15,000, and $8,000. The interest rate is 6%, and the transmission line should have a life of 30 years. A. What is the present worth for each estimated value? B. Use the range of estimates to compute the mean annual savings and then determine the present worth. And C. Does the answer to B match the present worth for the most likely value? Why or why not? So let's begin over here. And let me choose a nicer color. There we go. All right, so first for part A, let's find the present worth for the optimistic. And this is equal to negative 250,000 plus 20,000, which is my optimistic annual savings. And then we're going to do a P given A, 6%, 30. And this gives me 25,300. Great. Okay, so now let's do the present worth of the most likely. And this is very similar, but the difference is this number 20,000 is now 15,000. And if I do this, it turns out that I go into a very negative number, telling me that fluctuations, that this is probably not the best project. Fluctuations in the annual savings will cause major changes here in my decision. So, and guess what happens when it's pessimistic? Well, clearly this is going to end up being something terrible. Now, with sensitivity analysis, we talked about these fluctuations, but also from a more practical point of view, if it looks like your most likely estimate is going to be negative and your pessimistic goes really that low, that fast, then this is probably not a good project for you. Okay, so here we have three numbers: the optimistic present worth, the most likely present worth, and the pessimistic present worth. So what we're going to do is now we are going to use the range of estimates to compute the mean annual savings. So for B, the mean annual savings is equal to, let's remember that it is the optimistic plus 4 times the most likely plus the pessimistic divided by 6. So this is equal to the 20,000 plus 4 times the 15,000 plus the 8,000. All of it is divided by 6, which gives me 14,667. So now we're going to do our present worth using this number. So present worth using the mean annual savings, and this is going to be negative 250,000 plus this 14,667, P given A, 6% for 30 years, and this gives me negative 48,109. Okay, so now part C asks me to compare. Does the answer to B match the present worth for the most likely value? Why or why not? So here we see that it's actually worse if we go with the mean annual savings. And why would we even bother doing all of this? Well, as you can see, it's actually a little worse off than here. And now in this particular example, it turns out my decision would be the same with whether I use the most likely or the mean annual savings. But it is important to see that it is worse with the mean annual savings, because if we take into consideration that there is a probability that we could go as low as this is actually a more realistic number that takes into account that possibility. Okay, so and the reason that they are not the same is because, as I mentioned in the previous video, these are not, so 20,000, 50,000, and 8,000 are not perfectly even. So there's a difference between the 20,000 and the 15,000. There is a difference of 5,000, But between the 5,000, 15,000 and the 8,000, there's a difference of 7,000. So clearly this is going to be leaning more towards the negative, because the negative's a little further from the most likely than the optimistic. Okay, so let's continue. Now let's talk a little more about probability. There's a concept in probability called joint probability distribution. A joint probability distribution is needed to describe the likelihood of outcomes that combine two or more random variables. In other words, what is the probability that this thing that has a probability of let's say 50%, and this other thing that has a probability of 30% both happen at the same time. So if events A and B are independent, the joint probability for both A and B to occur is, and this is the notation, P, the probability for A and B is the same as the probability of A times the probability of B, which we know with decimal numbers will always give me a smaller number. So there's a smaller probability that they will happen together as a probability than the probability that they will happen separately. Now, why is this important for us? The reason this is relevant is because there's something called expected value. So expected value of a probability distribution is the weighted average of all possible outcomes by their probabilities. In other words, let's say, I'm trying to think of an example, but we'll have one here in a bit, but there's different potential outcomes. Okay, so let's say we have two different outcomes, and there is a 60% chance that outcome 1 happens, and there's a 40% chance that outcome B happens. And if outcome 1 were something numerical, so if there is a probability of a 60% probability that I will get $1,000 in this investment, and there's a 40% that I will get $500 instead, then my expected value would be 1,000 times 0.6 plus 500 times 0.4. Okay, the expected value represents a more, it's not that that's the number you're going to get. Clearly, I'm going to get either 1,000 or 500 and nothing in between. But the number I'm going to get is going to be in between those numbers. But what it represents is it's something that I can use to do a fair analysis with. Because if I make analysis with the 1,000, well, I could always get 500. And if I use a 500, I could always get 1,000. So this helps kind of even things out. So here we have an example. It says, Acme Manufacturing has installed a much needed new CNC machine. The initial investment in this machine is $180,000 and annual expenses are $12,000. The life of the machine is expected to be 5 years with a $20,000 market value at the time. Acme's MAR is, minimum attractive rate of return, is 10%. Possible revenues follow the probabilities given below. So we have, there is a 10% probability, or a 0.1%, 0.1, not probability. So this is 10% probability that it'll be $35,000 revenue, a 30% probability that it'll be $44,000, a 40% probability that it is $50,000, and a 20% probability that it is $60,000. Before we start doing calculations, we need to make sure that these numbers add up to 100, and we can see really quickly that they do. So it adds up to 100%, which is good, because remember that's one of the rules of probabilities, right? So if I want to estimate the savings here, what I'm going to do is, or no, not the savings, the revenues, I'm sorry. If I'm going to do this with the revenues, what I have to do is I actually have to multiply, I'm trying to look at my notes here and try to decipher some of the numbers. Yeah, anyway. So expected value is going to be, the expected value will be 35,000, and this is the expected value for the revenues. 35,000 times 0.1 plus 44,000 times 0.3 plus 50,000 times 0.4 plus 60,000 times 0.2, and this gives me 48,700. Again, this is an expected value, which doesn't say that that's what I'm going to get. What it means is it's the fairest way to use something in an analysis. So now let's calculate my present worth. and I'm going to say that this is negative 180,000 plus, now let's say it says that my annual expenses are 12,000, and I just calculated a more representative number for my revenue. So I'm going to do 48,700 minus this 12,000. Sorry for cramping things, and then times P given A, this number times that, not the whole thing. 10% for 5 years plus my salvage value, which is 20,000, which is going to be a P given F, 10%, oops, comma, 10%, 5, and it's going to give me negative 28,459. And that is my answer. So that's not a good investment. And again, since we have probabilities, it's important that we know how to do things like this, because it'll give us a good realistic look, but it's not this number. Remember, it's something to make a decision, not an exact number that we're going to lose. It's not an amount of money that we are going to lose. It is just a tool to help us make a decision. Oh, I had it here. Okay. All right, so let's see this example right here. One more. It says annual savings due to an energy efficient project have a most likely value of 30,000. The high estimate of 40,000 has a probability of 0.2 and a low estimate of 20,000 that has a probability of 0.3. What is the expected value for the annual savings? First of all, let me point something out. Here we're talking about most likely, high, and low. It might remind you of what we did with optimistic plus 4 times the most likely plus pessimistic divided by 6. This is not the same thing, because we're being given specific probabilities like 0.3 and 0.2. So we are not going to use this formula. This formula is we're supposed to use whenever we are not given the exact probabilities, by using a distribution that we think will work. Here we're being given 0.2 and 0.3 for this, but 0.2 and 0.3 don't add up to 1. What does that mean? Well, it means that the most likely value, for which I wasn't given a probability, must be equal, its probability must be equal to 0.5. So for the 30,000, it's going to be 0.5. For the 40,000, it's going to be 0.2. And for the 20,000, it's going to be 0.3. And now I can do what I did earlier, where I'm going to have the estimated savings are going to be equal, and that's all I'm being asked for. What is the expected value of the annual savings? This is going to be 0.3 times 20K plus 0.5 times 30K plus 0.2 times 40K. And it gives me 29,000. All right, excellent. We'll continue learning more about this topic on the next video.